So let's look at this example where we're going to apply Dalton's law. So this question talks about a sample of dry air. It gives a volume, it gives a temperature, and it gives you the moles of each component of the gaseous mixture, which is dry air. And the question is asking for you to calculate the partial pressure of all the gases in the mixture and then the total pressure of the gaseous mixture. So basically, what you need to do, let me go to my pen function here, is firstly determine the partial pressure of each gas. So the equation we're going to use is P is equal to nRT over V, and this is the equation we're going to use for each gas. So let's start with nitrogen. So the partial pressure of nitrogen would be equal to the number of moles of nitrogen, which is 0.0319 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees, which we have to convert to Kelvin, so that's 298 Kelvin. And then we divide all of that by the volume, and the volume is 1.00 liters. All right, so let me do that here, 0.0319 times 0.0821 times 298 divided by 1. So according to my calculations, this works out to be equal to 0.780. 0.780. And the units would be atmospheres because the liters will cancel out here and here. The Kelvin will cancel out here and here. The moles will cancel out here and here. And you'll be left with atmospheres. And then we do the same thing with oxygen. So let me do that here. The pressure of oxygen would be equal to the moles of oxygen, which is given as 0.00856 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times temperature. So the only thing that's changing as we do each of these would be the number of moles. Everything else is the same. The temperature is the same, and the volume would be the same. So let's do the calculation here for this one. 0.00856 times 0.0821 times 293 divided by 1. So this would give you 0.205. Do that here. 0.205 atmospheres. And then now the next gas is argon. So the partial pressure of argon. Now the number of moles in this case is 0.000381 moles times 0.0821 liters atmospheres over mole Kelvin times 293 Kelvin, all divided by 1.00 liters. And so let's do that calculation. 0.000381 times 0.0821 times 293 divided by 1. So according to my calculation, this gives you 9.17 times 10 to the minus 3. And I'm feeling a bit uncertain about this, so let me redo this one just to be sure. 0.00381 times 0.0821 times 293 divided by 1. Okay, actually this is incorrect. My suspicions were, let me just erase this here. So I was wrong about that. The actual answer is 0.09. Oops. Go back here. So the answer is 0.0917 atmospheres. And then the last gas is carbon dioxide. So the pressure of carbon dioxide would be equal to the moles, which is 0.00002 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature 293 Kelvin, and all of that divided by 1.00 liters. So let me do that calculation. So that would be 0.00002 times 0.0821 times 293 divided by 1. So according to my calculation, this works out to be equal to 4.81 times 10 to the minus 4 atmospheres. Let me do that again just to be sure. Times 293. Okay, so that's it. So those are the pressures for each gas, the partial pressures of each gas here, 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 and here. And then the question is asking for the total pressure. And the total pressure would simply be the sum of these. So let me just do that here, 0.780 plus 0.205 plus 0.0917 plus 4.81 times 10 to the minus 4. And the answer I got is 1.08. So P total will be equal to 1.08 atmospheres. All right, so that's basically how that example is done. All right, okay, so the next topic we're going to talk about is mole fraction. So until next time.